record, and we're back with another exciting Java course. And what I'd like to do today is get through this idea that we could have communicating Java programs over a network using the material in Chapter 43 called Remote Method Invocation. So in Java, what we have available to us is a mechanism whereby we can communicate our method invocations across a network using the marshaled concept of serialization to take parameters, move them across TCP/IP sockets, do an invocation, do a computation on an example, serialize the answer, and then take that serialized answer, transmit it back to the receiver in order to be able to do that computation remotely. What this means to me, the implication, or motivation if you will, for this entire technology is that I can take a bunch of computers, a network of workstations, and transmogrify them through my clever Java programming into a supercomputer, which allows me to do lots of computations very quickly over a network by virtue of being able to segment or divide my jobs into little chunks that can be done on the individual machines. Let me tell you that while that may be easy to say, it's not particularly easy to do. There are certain things which can be divided efficiently across multiple CPUs on a network. The number of things that can, I'll call it, be parallelized in this way is actually quite small. And so what we'd like to do is, first of all, examine the technology by which we can do the remote method invocation. There we are. I'm not even going to look at this screen because it just pisses me off. And then the other thing we're going to do is figure out how we can proceed through the divvying up of a program so that it can be remotely executed. So what I'd like to do is introduce you to this basic idea. First, we understand, I think, already about serialization, right? Can someone tell me, please, what is serialization? First I say, we all understand this idea, and then I ask what it is, and then I find out nobody understands the idea. What is serialization? Didn't we discuss this in the class? Do we need a lecture on serialization before we do RMI?
Like doing things in order.
No. That's when you do things sequentially. You're confusing sequential execution with serialization. Serialization is when you take an instance of an object and convert it into an array of byte. That is done so that you can achieve persistence. It's also done so that you can transmit the objects over a network. Right? So when we think about a stream, we think about an unformatted sequence of bytes. But when we think about an instance of an object, we think about something that has been formatted. And when we take that instance of an object and convert it into a sequence of bytes and push it down a stream, that means at the other end of the stream, this pipe, or socket, as you might call it, is going to be able to receive the object. Moving objects across a stream means being able to push them across a socket so that we can go across the network with our instances. So when we do remote method invocation, the first enabling technology that we must rely upon is serialization. Serialization is the way in which we marshal parameters across a network. So when we have a mechanism for doing the marshaling of parameters across the network, we have to be very concerned about things like type. Right? The data type that we transmit across the network is going to be well understood by the receiver. The data type of the answer that the receiver computes and then transmits back has to be well understood by the sender. So we'll have I'll call it master-slave relationship. The side that does the computation for us will be the slave, and the side that calls for that computation we can call the master. When we proceed to invoke a remote method on the slave, we can stop our primary I'll call it the primary thread of execution. So if we have a main method and it has a thread of execution and we do an invocation and we say something like A equals B, where B is getting computed remotely, then the left-hand side of the equal sign, the A, doesn't get assigned until the computation B is finished. That stops everything. It's a stop and wait protocol. So if you want to parallelize your code, you're going to have to do something like A equals B at the same time C equals D, and then try and combine the answers A and C. So if you can compute these things simultaneously, then you can take advantage of true concurrency. True concurrency is really different from multitasking. Right? Why?
Yes, it's between hardware multiple tasks.
Right. Every Windows operating system, every Unix operating system, every Mac operating system is a multitasking operating system. Right? That means you can have multiple tasks running, seemingly running at the same time. Seemingly being the operative word. You do not have true concurrency. Right? The number of CPU cores that you have on your machine is generally finite. Perhaps 2 or 4 or 8 on the outset. You don't really run multiple tasks simultaneously unless they've been divvied up across the different cores. So in general, if you wanted to run 1,000 different tasks at the same time, you couldn't do that on a single box with perhaps a couple or 4 cores. You just couldn't do it. So how would you obtain true concurrency? Well, that's when you have multiple computers all working at your beck and call at the same time. And that's the power of using remote method invocation. So what you'd want to do is come across with something like a segmentable task. Can anyone give me an example of a parallelizable task? Task that you could break up. What's a task that you could partition?
Multiplying two arrays together like that.
Sure, you could do array multiplication that way because you've got rows that have to be multiplied by columns. If you took all the rows and you took all the columns and you took them and separated them out and send them off to the different machines for computation and have them come back to you, they can be reassembled and added, and then of course you would have your answer. What would be a problem with doing that kind of parallelization across a slow network?
Do a lot of stuff to transfer.
Yeah, you would become I/O bound. Their overhead in doing that would be so high that 10 computers would not make you 10 times faster. 10 computers might only make you 1.5 times faster. So you might not be able to get away with doing that particular operation if you have a high latency network with a poor quality of service. But there might be other things you could do. What else could you try and do? No ideas? How about movies? Right? If you say, I want you to compute frame 0, I want you to compute frame 1, I want you to compute frame 10,000. All the frames are being computed independently of one another, and then as the images come back, you can just assemble them into an image sequence on the disk. So if every frame takes like an hour to compute, then presumably 10 machines could compute frames at a rate of 1 every 10 minutes. Maybe 100 frames could be computed by 100 machines at a rate of perhaps 1 frame a minute. In other words, you could get good scale when your CPU becomes bound to the task, so you're not swamping your network. So if you can remain, let's say, CPU bound during the task, then you can have a efficiently parallelizable system. All right, that makes sense, doesn't it? Yes. So let's think about this in terms of, let's say, image processing. Suppose I had an image, and I said, well, I want some image, low-level image processing to be done on the top half of the image. I could give that to one machine, and I could give the bottom half of the image off to another machine. So some kinds of image processing that take a long time, that might be a good thing to parallelize. Parallelize. Distribute. So here is the RMI protocol. I've got a client and I've got a server. The server is doing my computation. The client uses remote method invocation to talk to the server, and the client talks to a registry in order to discover the server. And the registry is nothing more than a web server running on a fancy port, which comes back and tells us about services that are available. So the registry is a separate JDK job that you can start, and you can find it inside of the Java Development Kit binary directory. It's called registry. And you could start it from the command line, or you could start it from within your Java virtual machine. So when we think about the registry, what we really think about is a domain name server for processes that are running on your slave. And your slave is going to essentially go to the registry and say, hey, I've got a job and a service, and I want to advertise it. So the registry, in a sense, it's like a phone book that lets you look up stuff. And so now I'm thinking about this registry, and I think about it, and I think, well, geez, how does the server know about it? How does the server know where the registry is? Does the registry have to run on the server? Its domain name services, they can run anywhere. So how would the server know about the registry in order to register itself? Moreover, how would the client know about the registry in order to find services? Well, the registry runs on a machine. It doesn't have to run on the client. It doesn't have to run on the server. It can run anywhere. So as a result, you have to know where the registry is in advance by virtue of its IP address or its machine name. Moreover, there are common ports that are used for the registry. 1099 is the common port. And so it's a non-reserved port, a high-numbered port, a port that you can essentially occupy on just about any machine. You can listen for connections on this port. And you can run it anywhere you like. You, as a Java student who is running perhaps your first RMI program, will probably end up running it on the same machine you're running both the client and the server. Because when you try and run a toy problem, last thing you need is to add a whole bunch of machines to it, especially when it's your first time through. So while that may be a convenient thing to do, it's certainly not necessary. There's another thing that goes on when you're dealing with remote method invocation. The goal is to be able to invoke a method that looks like it's local on your machine, but really isn't. So to make that method look like it's local, you have to create what's called a proxy. The proxy for that method, well, it looks just like a method, only with a difference. And the difference is it can throw a remote exception. And the remote exception can be thrown because, in a sense, what you're doing is you're trying to communicate across what we're calling the remote reference layer, which is a layer on top of the transport layer. Remember the layers? Does anybody remember the layers, the 7 layers? Say it again?
I liked it.
You like the 7 layers? The physical layer, the data link layer, the network layer, the transport layer, comes after?
Session.
Session layer. Oh, geez, is he reading it? And then what happens, Kyle?
Presentation layer.
Oh, the presentation layer. And then what happens, Kyle?
Application.
This is great. The application layer. Okay. And tell me again, what does the transport layer do?
Send you back to the remote reference.
You're killing me here.
Recovery, error recovery, and flow control.
Flow control. It's the pipe. The data that goes in order comes out in order when you're dealing with TCP on top of IP. But when you're dealing with UDP over IP, you have a connectionless protocol, and datagrams go in one order and they can come out in any order. So Internet Protocol, or IP, that's where those interesting and wonderful TCP IP addresses are being assigned. But TCP, that's where you get what we call the sockets layer. That's where streams are obtained for transmission and for reception. So at the end of the day, when we start to work at this remote reference layer, what we're really doing in here is we're taking the instances that have been serialized and passing them across the TCP IP layer. The stubs and the skeletons represent what I call the proxy. So the stubs, which are created on the client, handle all of the communications through the remote reference layer. The skeletons receive these communications and then communicate to the server so that instances can be invoked remotely. And what you have to do when you invoke those instances remotely is you must try and catch the remote exceptions that may be incurred. So here on the client, which I'll call the master, the instigator, we send what they call marshaled parameters. And marshaled, when we look at marshaled parameters, think serialization. That means you're taking the arguments to the methods and you're serializing these arguments. Primitive data types, do they have to be declared as serializable?
I hope not.
It's a trick question. You can't declare them as serializable because they're not reference data types. Primitive data types, can you serialize them?
Oh, can you turn them into a reference object and then serialize them?
You could. Do you have to?
Can you just raw data?
Yes. Ints get converted into 4 bytes. Shorts get converted into 2 bytes. Chars get converted into 2 bytes. In other words, all of the primitive data types can be serialized without being declared as serializable. But any other reference data type you plan on marshalling as a parameter, that must be declared as serializable. You must implement the serializable interface. And what about the return values? Do they have to be serializable?
Not if they're primitive data type.
Well, all primitive data types are already serializable. You just don't have to declare them. So the answer is yes. Everything gets serialized on the return. You can't declare primitive data types as serializable because they're primitive. They can't implement the serializable interface because they're primitive. What you can do is you can serialize them. So here's the deal. We make an invocation to the proxy, which we call here the stub. The TCP IP link runs through the application layer. The skeleton deserializes. The server does a computation, returns an answer, comes back to the TCP IP link, and does a return then from the stub. So this equal sign blocks the primary thread of execution and does not give you an answer to the left-hand side with an assignment until after the computation is done. This is stop and wait protocol. Throughput falls to 0 from the client point of view until after the equal sign returns, which is why it's so important to embed the equal sign inside of some thread so that you can do other things at the same point. Yes, sir?
So you said stop and wait. You deploy that return to continue operation.
Yes.
But is the protocol or the operation itself, can you go from asynchronous
If you want to invoke this asynchronously, that is the equal sign, you need to embed it in a thread. You must be explicit about it, and you must basically know what you're doing. Because if you're going to allow this equal sign to just hang there inside of a thread until it returns, in general, you'd better know how to deal with it when it does return. You know, what should I do with x after the computation that's been asked for has been supplied? And if the answer is, you know, it fits somewhere in a giant equation parse tree, well, then you can then let the equation parse tree proceed. Have people seen equation parse trees before? It's not a particularly complicated idea. Let's see if we can do this. New slide. So consider the parse tree. What happened? Parse tree. Huh, that's weird. Now, how do I make, like, text happen here? This is terrible. I feel like I don't know how to use, like, computers whenever I sit down and use Word. It's like a new experience here. Text box, is that it? There we go. Geez, that's weird. Okay, so suppose I said something like this. Y equals, that's little, isn't it? mx plus b. Okay? At the center of the tree, and this is kind of small, so I'm going to, here, y equals mx plus b. So at the center of the tree, I see plus, and now on the left-hand side, I see times x, and on the right-hand side, the child is b. And I can't really invoke the plus sign until m is multiplied by x.
Oh, I do know what this is, actually.
Right?
Yeah.
So what I do is I say, let's let the CPU1 compute m times x, and then when it returns an answer, I can then take it and add it to b. So in effect, what I'm doing is I'm saying, because of the order of precedence in the equation, I'm able to decide, for more complicated equations than this, obviously, where to segment the problem in order to be able to say, okay, you go compute this, you go compute the other thing, and when it comes back, we'll be able to add up all the answers together. So under I'll call it the Java Development Kit deployed environment, you have a binary directory with a series of exe commands. And those commands include the RMI registry, which we already talked about. That's our little domain name server for tasks inside of RMI. And there's also a thing called an RMI daemon. And that's part of what we call our RMI runtime. So now I've got a mechanism whereby the server has been removed from the client via the registry interface. And the server has to go to the registry in order to tell the world about its services. And the client has to go to the registry in order to find out about the server. And the registry can run on any machine you like. So if the machine for the registry is well known and reachable, we should be able to use standard protocols in order to be able to find out about the server. That is, in order to go through the process of discovery. So there are, I'll call them little recipes or procedures for doing remote method invocation. And what you want to do is you want to create some sort of a proxy that you can invoke remotely. And that proxy is going to contain the methods for the server to implement. But it's not going to have the implementations. So you have to have interfaces for the remote classes without implementations. Then you're going to compile those interfaces, and you use a thing called the Remote Method Invocation Compiler, or RMIC compiler, and what that does is it creates the stubs. and those stubs handle the marshaling of data across the network. Then what you do is you create a server application and compile that. You start your RMI registry, start your server application, and then you can run your little client, and the client will proceed to discover the services in the registry and then do the invocation. And then, of course, you want to test. So, Rado. Sorry, I got my alarms. So, where can we find more details about this?
Website.
Well, there's a bug. Can read the bug. What chapter would that be? Yes, sir.
Can you post your PowerPoints online and not that you upload them?
You could do, but what I was thinking is that you might find this is all in the book.
No, but your PowerPoint like breaks down those
Okay.
things into one thing.
Yeah, I mean, if you looked at chapter 43, I think you would find that's where these PowerPoints kind of came from. Let's see if we can find some of these things. Because I think if we do this, I have so much trouble using this resolution on my screen here. It's maddening. Can you look over here? Bear with me a moment while things get started. You know what I was thinking is that pretty soon we'll take a break, and during that time I'm going to fix this monitor so it doesn't look so crummy. Is there anybody here who actually knows how to use like these Windows computers? Nope. It's my fault for using Windows. Okay. So what I've got here is a little example that uses an RMI registry. And what this does is it calls locate the registry and create registry. Locate registry.create registry essentially starts an instance of the RMI registry on the local machine and assigns it a port. In this case, I'm giving it a non-common port called port 9999. And so then what I can do is I can go into this registry and bind services to the registry by name. So when somebody wants to find these services, they not only have to know my IP address, they have to know what port my registry is running on. So you would have to know in advance the IP address of my laptop. Even worse, you'd have to be on the same local area network as my laptop, which might mean being on the student network. And then you'd have to know the name of the service, and it says, here's my find service, and each name will be different because I'm going to associate with this string the number I, whatever that is, will be 0 through 9 apparently, so there'll be 10 little services, and they'll all have some remote object associated with them. I'll be able to print out I created a registry. I'm going to hit return over here so you can see what's on the other side of this equal sign. There you go. I have the implicit IP address for the local host. That's like 127.0.0.1. I've got a port number where the registry is being run. So that's going to enable me to open up a socket connection to the registry while it's running inside of my machine. I'm going to then proceed to look up the registry based on this variable that came back on that machine, and that will return a remote registry instance. Then I'm going to go to that remote registry. I'm going to list all of the services that are running on it. Remember, it's just a directory service. So it's listing services that are running on the machine. Then I'm going to take that list and I'm going to say, here's a bunch of things that I found on that registry, and I'll print them. So I'm going to use this machine to start its own registry, create a whole bunch of services, which don't really do anything, and then proceed to list those services. Now the question of whether or not this works is another matter. I just rebooted the system, and I didn't actually put it on a network. I'm thinking something bad will happen. Oh, I'm getting a spinning doodad at the bottom as it compiles. Oh, it actually worked. How about that? How about that? So he went out. I have an IP address for my local host. I've got a port number. He came back with a remote registry with an object ID. And then he proceeded to list all the services that are running on the registry. Sweet. How about that? Is this break time now? I feel like it's break time because I want to fix my computer. So why don't we take a little break while I have a little quality time with my laptop here.